All right, we've looked at uniform rods, uniform arcs. Now we want to handle non-uniform mass distributions. So we're going to start with a non-uniform rod, perhaps something that looks a bit like that behind me. Give me just a second. All right, and let's talk about this on screen. So imagine we have a mass density that's varying linearly, and I believe, I'm just going to confirm, this is workbook problem 9.33. Yeah, so this is very similar to workbook problem 9.33. And what I'm going to do is I'm going to let the mass density be this function. So the density is now a function of x. And so as we move from the left end of the rod to the right end of the rod, we expect the mass to increase. All right. And again, we're starting with the left end at 0, and the right end is going to be some distance L equals 5 away. I'm still going to split this up into 5 spheres. And for now, I'm just going to let K be some number 1. In some other problem, it might be a different number, like 3.2, whatever. Now, our goal should be to try and make a visualization of this that helps people understand. So it's not enough just to draw the objects in place. We also want to kind of add some physical meaning by showing the density of the balls also vary. So we'll handle both of these things. But again, yeah, basically x here, as x goes up, we'd expect this function to get bigger, and we expect more density. So how does this look in the code? All right, so let's get in there and take a look. All right, and so here we go. So what I've done now is, instead of having mu up here, we've got a linear mass density constant. So that's the new piece, and we're still doing a 5 and a 0, and this is still going to be over there. Okay, great. So, all right, next. We come into here, we're going to draw the guide. Its left end is at the minimum position. The axis is rod length. In this case, you could actually use X max, but in general, rod length is better because that's the actual length of the cylinder. So, and this will work even if X min is not equal to 0. So that's good. Draw some coordinates, initialize some parameters here. Same as before. Here's our loop. So we're going to go from the minimum value to the maximum value in increments of dx. To remind you, dx was the rod length, which was 5, over the number of spheres, which is 5. So we should be going in units of 1. All right. So we're going to draw the ball. Again, I'm going to draw the ball's position. I'm going to first draw a ball, then move its position. The computer will do this so rapidly we don't even see it move. For right now, I'm just going to set the ball's opacity to 1. Full color, we'll deal with that later. If you want, I guess you could do 0.5, but for now I want to use 1. And let's think, what is the computer going to do? When it comes in here, x is a new parameter. It's going to set it to x min, which is 0. It's going to head towards x max, which is 5, in units of 1. So the first ball will be drawn at x is 0, and then we're adding to that 0.5. So the first one will be drawn at 0.5. Then the next time, we're going to increment by 1. The next one will be drawn at 1.5. And we're going to keep going up, 2.5, 3.5. We're almost there, 4.5. The next one won't be drawn because the next one, if we keep going up, x would equal x max, and that's going to cause us to spit out of the loop. So remember, when x equals 5 for the last iteration, it will not draw the sphere. Okay, so it's not going to draw that last sphere. It's a strict less than in here. So it has to be less than that maximum range. Okay, so that makes sense. The issue is, how do we figure out the ball's mass? So we know it should be this in general. By this, I mean, we expect it should be linear mass density. Now here we want to be a little bit careful. Linear mass density for us, you would say, is K star X. And this will get an approximately correct answer. However, remember, the ball's position is not actually at X. It's been shifted over a little bit. So if we want to get this thing correct, we should actually use the ball's position.x, right? This is the X coordinate of the mass we are drawing. Whoops. Oh, this part is a part I'll explain in a minute. We'll do that later. Just give me a minute. Sorry about that. Okay, and so now what is it going to do? It's going to go into here, find the ball's X coordinate, use that to get the density at the location of this ball, and then do the density calculation just the same as usual. Cool. So when we run this one, let's see what this looks like. All right, and so we see, maybe this makes sense to you. If this ball is more dense than that ball, I hope it makes sense that the center mass starts to get shifted over. Okay, so the original center mass was right in the middle here. Now it's been shifted over. Now it's getting a little bit hard to see. All the rest of that we're going to do right now is cosmetic, but this gets the job done. So let me clear out those drawings. And I suppose we could see if the percent differences are okay. Notice this is actually a pretty small percent difference. And this was working out as well. Again, I did theoretical calculations using problem 9.33. So you could do those and code in what these should be to get a percent difference. So you could do a little calculus to figure out the theoretical values. All right. Going back into here, I want to deal with the coloring now. I know this seems silly to waste time on it, but if it makes it easier for other people to understand, maybe it isn't so silly, right? If it means you can communicate with other people more rapidly by putting a little effort into your presentation, that is probably worth it. So what I'm going to do is I'm going to create a new thing called DM max, and I'm going to set that equal to 0. This is a counter. Initially, the counter is at 0. So at this point, we haven't gone into the loop. We haven't made any spheres yet. So right now, the maximum mass that we have for any of the balls is 0. And so what I'm going to do here is in this line of code, I could easily go in and add this. If the ball that I just drew, if that ball's mass, whoops, dm, is greater than my existing value of dq max, this is called an if statement. It's going to check this condition. If this statement is true, so if my current sphere's mass is larger than what I've stated is the, whoops, I think I want to call this dm max, not dq. Yep, okay, got it. If the ball's mass is larger than that largest value, I want to replace it. So I want dm max to equal that ball's mass. And that's it. So the computer will check this. And then for this particular code, that should always be true. And so if you wanted to see this, okay, so what I'm going to do is I'm going to print all the masses of the spheres as we go. And then in addition, we could say down here, I could say outside of the loop, I could say print dm max. And just so I could make this clear, let's put in some quotes. All right. And so now we should be able to clearly tell, again, there should be 5 masses printed here or something like that. And then maybe it'll be 4. I don't know. I haven't thought it through in the loop. So in this case, hopefully we'll see this print out. So let's run this now. So if we go into here, we see the first mass. This makes sense. We see the masses creeping up. And then notice we see the maximum mass is right there. So great. So we know this is computed correctly. That's good. Now I don't need this print statement, so I could take that out so I don't waste time, but maybe we'll leave it. So here's where the for loop gets really cool. So I'm going to say for let's say ball in rod. Whoa, what does this mean? This is going to say, give it a name called ball, or you could, if you want, we could call it my ball here, just so we're not getting confused. So I'm going to go through the rod, which is a list. If you recall, it's a list. It's like this. However, for this type of for statement, we don't need those square brackets. So I'm going to go through the list, and I'm going to pick each element of the list. Now, I happen to know in advance that the elements in the rod list are balls. So I'm going to say for my ball in the rod. So it will go through and pick out each single one. And what I could do is I could say, let's change the ball's color to a vector 1, 0, 0. That'll be red. That'll change it. And let's change the ball opacity to equal its proportional to its mass divided by the max. So the idea is if the ball's mass is small, right, we should get, oh, and let me just scoot down a little bit so you can see that there. If the ball's mass is small compared to dm max, it should be nearly invisible. And when we run this, we see it's popping out here. Oh, let me see here. What did I forget? Let's see. All right, let's try this. Oh, geez. This is my fourth take already. I probably won't re-record this, so I apologize. Let's see if I've made a mistake here. Let's try that. Yeah. Oh, I see. So I have to give this the same name. So let's try it this way. The problem was it went through and the last ball that was in the previous list was called ball. So it colored the last one correctly. But so now if I want to go through everyone in the list, I actually have to use the same term here. So I'm sorry about that. Hopefully this runs or else I'm in trouble and I got to do another take. And so, all right. So now I better check. It looks like, I know what I forgot. Hopefully you do too. Whoops. I forgot a my ball right there. So what it was doing is again using I screwed up there. So sorry this took so long. Come on today. All right, so it's having some trouble. I'm going to hit Control C. When it rains, it pours. Now I'm going to hit refresh. I'm going to make sure I hit Control C. I'm going to refresh this. For some reason, it's having trouble saving there. Let's go into here. Control V. All right. So let's get up there. Let's run this program. There we go. Finally, third time is the charm. And so we could see this, if I could zoom in a little bit, just to get it all on the screen. You can see the spheres are there. We see the center of mass location. This is just one way to do it. But, and hopefully, again, you can see there's kind of the maximum and the percent difference and all that stuff. And again, from workbook problem 9.33, it shows you all the theory on how to get that. All right, let's go ahead and call that good.